Dark matter is a type of matter that is thought to exist in the universe but cannot be directly observed. Astronomers estimate that only about 5% of the total amount of matter in the universe is visible matter. The remaining 95% consists of mysterious components called dark matter and dark energy. Dark matter, as its name suggests, does not reflect, absorb, or emit light, so it cannot be observed directly. However, the existence of this type of matter has been indirectly determined by phenomena such as observed galaxy motions, cosmic microwave background radiation, and the formation of large-scale structures. The rotation rates of galaxies are higher than predicted based on the visible matter they contain. This suggests that there is an extra gravitational effect holding the galaxies together. Dark matter is one candidate thought to be responsible for this extra gravitational effect. Dark matter can exist in two different forms: cold dark matter, which is thought to consist of fundamental particles, and fast-moving hot dark matter. It is not known exactly what it is, but scientists are conducting experiments and analyzing observational data to investigate dark matter. Dark matter has a major impact on the formation and structuring of the universe. Many observable phenomena, such as galaxy formation and evolution, the formation of cosmic structures such as cosmic filaments and large voids, the movement of galaxy clusters, and the interaction of black holes, point to the existence of dark matter. However, dark matter is an area that still contains many unknowns. Scientists continue to work to learn more about the nature, interactions, and formation of dark matter particles. It is important to study the discovery of dark matter, a phenomenon that appears to explain the movements and structures observed in the universe. Dark matter cannot be observed directly because it is invisible, and therefore it is a very difficult subject to discover. However, some observations and calculations reveal the existence of this mysterious substance. Dark matter was first noticed in the early 20th century when a problem arose in explaining the rotation rates of galaxies. While the stars in galaxies moved more slowly towards the outer parts during their rotation, the observed rotation speeds were not sufficient to explain this situation. This showed that an invisible substance was needed in the outer regions of galaxies. Fritz Zwicky is a scientist who played an important role in the discovery and understanding of dark matter. Zwicky is a Swiss-American astronomer and astrophysicist. He proposed the theory of dark matter by studying the motions of galaxies in the 1930s. Coma cluster, Zwicky noticed an inconsistency in the motions of the galaxies. Based on the rotation rates of the galaxies, he observed that the total mass in this cluster was too high to be explained by visible matter alone. As a result, he posed the extra mass problem, and suggested that an invisible substance was needed in galaxies. Zwicky became one of the first scientists to introduce the concept of dark matter. Proposing the theory of dark matter, he stated that an invisible substance was needed to explain the anomalies in the rotation speeds of galaxies. Additionally, this discovery contributed to an important understanding of the structure of galaxy clusters and the formation of the universe. Fritz Zwicky's work on dark matter has become one of the cornerstones of modern cosmology. His discoveries and predictions have been supported by further research into the existence of dark matter and the important role it plays in the universe. Zwicky's work attracted the attention of the scientific community on dark matter and increased the momentum of dark matter research. Further evidence of dark matter emerged in the 1970s with observations of galaxy clusters and the rotation curves of galaxies. British astronomer Vera, by measuring the rotation rates of galaxies, Rubin and his colleagues discovered that the outer regions of galaxy disks also rotate faster than expected. These observations showed that there is more mass in addition to the visible matter at the center of galaxies, and that the source of this mass may be dark matter. Albert Boesma, in the 1970s, he is a researcher who supports Vera Rubin's work. By examining the rotation curves of galaxies, he showed that the outer regions of galaxies also rotate faster than expected. Known for his work on the cosmic microwave background radiation, James Peebles made important discoveries about the structure and composition of the universe. He developed cosmological models that predicted the existence of dark matter and emphasized the role of dark matter in the formation of the large-scale structures of the universe. George Smoot and John Mather are two notable astrophysicists known for their discovery of the cosmic microwave background radiation. In 1992, a research team led by Smoot and Mather was sent into space to measure the cosmic microwave background radiation using a satellite called COBE. The cosmic microwave background is radiation that formed in the early universe, approximately 380,000 years after the Big Bang. This radiation allows us to have important information about the evolution of the universe. By precisely measuring the distribution of the cosmic microwave background radiation and temperature fluctuations, Smoot and Mather's work became a major discovery about the formation and structure of the universe. This discovery made significant contributions to confirming the Big Bang theory and deepening our understanding of cosmology. George Smoot and John C. Mather won the Nobel Prize in Physics for this work in 2006. This award was given to them for the discovery of the cosmic microwave background radiation and their contributions to cosmology. Smoot and Mather's work contributed to our development of an in-depth understanding of the origin and structure of the universe and was an important milestone in the field of cosmology. Many experiments and observations have been carried out to determine the nature and composition of dark matter. Large Hadron high-energy particle accelerators such as the Collider have conducted experiments aimed at discovering dark matter particles. Additionally, observations have been made examining the large-scale structures of the universe, such as galaxy clusters, galaxy collisions, and cosmic microwave background radiation, to study the gravitational effects of dark matter. Observations have shown that dark matter is widespread in the universe and plays an important role in the formation of large-scale structures of the universe. While only about 5% of the total amount of matter in the universe is visible matter, the remaining 27% consists of dark matter and the remaining 68% consists of another mysterious component called dark energy. Observations and findings of dark matter. Since dark matter is a substance that cannot be observed directly, its findings are obtained indirectly. The rotation rates of galaxies are higher than expected based on the visible matter they contain. This indicates that there is an additional source of gravity around the galaxies. Dark matter is a possible candidate for this additional source of gravity. Observations of galaxy velocity distributions are one of the evidences for the existence of dark matter. Galaxies is important evidence showing the existence and influence of dark matter. Stars and gas, which belong to normal matter, generally concentrate towards the center of a galaxy, while dark matter is distributed around the island. This affects the velocity distribution of the galaxies. The velocity distribution of galaxies shows how the velocities of stars and gases on the island are distributed. The gravitational effect of normal matter accelerates the stars towards the center of the island, while the stars around the island have slower velocities. However, observations have shown that the velocity distributions of stars and gas in galaxies differ from what was expected. The reason why the velocity distributions of stars and gas in galaxies differ from expected is the effect of dark matter. Dark matter is found in large regions around galaxies and attracts stars and gas with its gravitational pull. This gravitational effect causes the stars and gas around the island to have higher velocities. Observations have revealed that the velocity distributions in galaxies vary in a characteristic way, indicating the presence and distribution of dark matter. In particular, the observed velocity distributions were consistent with models used to predict the presence and amount of dark matter. Large-scale structures in the universe are driven by and contribute to their formation by dark matter. Structures such as galaxy clusters, superclusters, cosmic filaments and voids are formed by the gravitational influence of dark matter. These structures are identified by observations and support the existence of dark matter. Cosmic microwave background radiation from the early universe provides information about the general structure of the universe. Detailed maps show that the distribution of matter in the universe is uneven in the presence of dark matter. These observations reveal that dark matter shapes the large-scale structure of the universe. Gravity lensing is an observation technique used to confirm the existence and distribution of dark matter. Galaxies or clusters of galaxies with large masses can bend light, distorting distant sources behind them. This distortion is an important observational tool in determining the existence and distribution of dark matter. Gravitational lensing is an important tool for determining the presence and distribution of dark matter. The gravitational effect of dark matter can bend the path of light and distort the image of a distant source. Gravitational to this event, it is called lensing. Gravitational lensing is a method used to detect the presence of dark matter and map its distribution. When a light source passes through a region with a high concentration of dark matter, the path of the light is bent by the gravitational effect of the dark matter and the source appears distorted. These distorted images can be used to determine the presence and distribution of dark matter. Because gravitational lensing provides information about the density profile and distribution of dark matter, depending on the shape and degree of distortion caused by the effect of dark matter. Observations and analysis. Gravitational showed that the number and properties of lensing events confirm the existence of dark matter. In particular, the gravitational effects seen around galaxy clusters, which are large-scale structures, lensing events indicate that dark matter is concentrated in regions where its density is high. Gravitational lensing events can be combined with many observational methods used to map the distribution of dark matter and confirm dark matter models. For example, gravitational effects combined with anisotropies of the cosmic microwave background radiation by analyzing lensing events. More detailed information about the distribution of dark matter and the structure of the universe can be obtained. In this way, gravitational lensing allows us to gain a greater understanding of the existence and influence of dark matter. Future observation projects and technological developments will enable a more detailed examination of lensing events and a better understanding of the nature of dark matter. Scientists use computer simulations and cosmological models to understand dark matter. These simulations mimic dark matter distribution and evolution, which is consistent with observations. Simulations allow us to understand the influence of dark matter on the formation of structures in the universe and confirm theoretical predictions. Dark matter has significant effects on galaxy formation and growth. It creates regions of high density and allows normal matter to come together under the influence of gravity. It triggers the accumulation of normal matter in these dense regions, and this accumulation initiates galaxy formation. The gravitational effect of dark matter can shape the different structures of galaxies, such as disks, centers and clusters. It also plays an important role in explaining the rotation rates of galaxies. Observations show that the rotation speeds of galaxies are higher than expected based on the visible matter they contain. These velocities are explained by the additional gravitational effect of dark matter. Dark matter contributes to the growth of galaxies by ensuring their rapid rotation. Additionally, it plays a critical role in the formation and growth of galaxy clusters. Galaxy clusters are defined as structures containing large amounts of galaxies. The gravitational effect of dark matter enables the formation of galaxy clusters and the growth of these clusters. Galaxy clusters are the regions where the concentration of dark matter is most evident. Large-scale structures in the universe are formed by the presence and influence of dark matter. Cosmic filaments are known as long fiber-like structures that connect galaxy clusters and where the concentration of dark matter is most prominent. The gravitational effect of dark matter supports the formation of these filaments. Large voids are areas where dark matter is less abundant. The gravitational influence of dark matter affects the evolution and growth of galaxies. Galaxies can accumulate more matter and grow in regions where dark matter is concentrated. The gravitational effect of dark matter ensures that galaxies stay together and maintain their structure. Dark matter has indirect effects on hot gas and star formation. The pull of dark matter promotes the condensation of gas and the collapse of clouds of hot gas. This collapse process initiates star formation. Thus, dark matter has a decisive influence on the formation of stars and the development of galactic disks. Dark matter and dark energy are two important components that play a decisive role in the expansion of the universe. The expansion of the universe is generally based on the Big Bang theory, and this expansion process is affected by dark matter and dark energy. Dark matter has a different structure than the normal matter found in the universe and therefore cannot be observed directly. However, dark matter is a component that interacts through the gravitational force. The gravitational effect causes dark matter particles to come together and form regions of density. These density regions also trigger normal matter to come together and support the formation of galaxies. Dark matter holds galaxies together under the influence of gravity and contributes to the formation of galaxy clusters. This creates a resistance to the expansion of the universe. In other words, dark matter has the effect of slowing down the expansion of the universe. However, the most dominant influence on the expansion of the universe is provided by dark energy. Dark energy is a component that accelerates the large-scale expansion of the universe. Dark energy is a mysterious form of energy that is distributed homogeneously throughout the universe. This energy accelerates the expansion of the universe by increasing the rate at which it is receding. Dark matter and dark energy together have a decisive influence on the expansion of the universe. Dark matter slows down the expansion of the universe, while dark energy accelerates the expansion of the universe. These two components allow us to understand the dynamics of the expansion of the universe and are an important source of information about the evolution of the universe. Dark matter is a substance commonly found in the universe, but cannot be directly observed because it does not interact with electromagnetic radiation. In contrast, we observe that dark matter has significant effects on normal matter and light through its gravitational effect. Various theories and hypotheses have been proposed regarding the content and composition of dark matter. According to the cold dark matter theory, dark matter consists of cold and slow-moving particles. One of the most common theoretical candidates are particles known as weakly interacting gravitational particles. These particles may have different properties than the particles described in the Standard Model and may be resistant to electrical or nuclear interactions. Hot dark matter theory is another important topic. These substances consist of fast-moving and low-mass particles. These particles, like neutrinos, are candidates for hot dark matter. However, neutrinos are not thought to be sufficient to fully explain dark matter. According to the extreme cold matter theory, dark matter particles consist of particles at very low temperatures and moving extremely slowly. It is not yet known exactly what these particles are and what interactions they have. The accidental matter theory is a theory put forward on the composition of dark matter. According to this theory, interactions can occur between dark matter particles. These interactions can affect the behavior and distribution of dark matter. This theory could help explain observed phenomena of dark matter. To obtain more precise information about the composition of dark matter, scientists conduct research using laboratory experiments and observational data. Important experiments and observation projects can help us understand the nature and composition of dark matter. The way dark matter interacts is also not fully known. Since it is closed to electromagnetic interaction, it is thought to be a component that does not interact with light and does not leave a trace in the electromagnetic spectrum. However, it is observed that it has effects on normal matter and light due to the effect of gravity. It is thought that dark matter promotes the formation of galaxies, enabling normal matter to come together and affecting galaxy movements. The nature of dark matter and the ways it interacts are still active research topics. Scientists are trying to detect dark matter particles in high-energy experiments such as the Large Hadron Collider. Dark matter and dark energy are two different components that have different roles and effects in the universe. Although it is difficult to say that there is a direct relationship between the two, They are interconnected in understanding the expansion and structure of the universe. Dark matter is a component of normal matter found in the universe that interacts with gravitational effects and does not interact with observable light. Dark matter ensures the formation and cohesion of galaxies, is effective in the formation of large-scale structures spread throughout the universe, and has a slowing effect on the expansion of the universe. On the other hand, dark energy is a form of energy that accelerates the expansion of the universe. Dark energy is distributed homogeneously throughout the universe and has a positive energy density. Therefore, dark energy acts as a driving force against the expansion of the universe and increases the rate of expansion. Dark matter and dark energy are generally considered together, although they have different effects on the expansion and structural formation of the universe. Due to its effects on the expansion of the universe, dark energy determines the large-scale structure of the universe, while dark matter enables the formation and cohesion of galaxies. However, the relationship and interaction between dark matter and dark energy are still not fully understood. Scientists are conducting further research into the nature of these two components and their effects on the expansion of the universe. These studies aim to provide more information to help us understand the structure, formation and expansion of the universe and to solve the mystery of dark matter and dark energy. The nature and properties of dark matter remain largely a mystery. However, future new discoveries and developing research methods are promising for understanding dark matter and elucidating its nature. The sensitivity of detectors used in direct detection experiments and data analysis methods are constantly being improved. Thanks to more sensitive detectors and advanced data analysis techniques, there may be a better chance of directly detecting dark matter particles. Next-generation experiments aim to examine the nature and interaction properties of dark matter in more detail. Observational data are an important resource for understanding the effects of dark matter in the universe. Advancing technologies and telescopes will allow us to observe the motions of galaxies, the distribution of galaxy clusters, and the cosmic microwave background radiation more precisely. This could help us study the distribution and effects of dark matter in more detail. Scientists are investigating the nature of dark matter and its effects on the expansion and structural formation of the universe through simulations and theoretical models. More realistic simulations can be achieved thanks to developing calculation methods and supercomputers. Big data analysis and artificial intelligence methods play an important role in dark matter research. Future research will leverage these techniques to more effectively analyze more complex datasets. Artificial intelligence algorithms can be used to identify signatures of dark matter, map its effects, and detect dark matter particles. It is important to combine various observation methods to better understand the nature and effects of dark matter. For example, cosmic microwave background radiation, galaxy motions and gravitational. More comprehensive information about the distribution and effects of dark matter can be obtained by combining different observation techniques such as lensing. In addition to existing theories about the nature of dark matter, it is also important to develop new theoretical approaches. These approaches may focus on alternative models and hypotheses to explain the properties of dark matter. New theoretical approaches may help us understand the nature of dark matter and confirm its existence. Future space missions may offer new ways to observe and understand dark matter. Telescopes and sensors with more advanced technologies in space may allow us to collect more data about dark matter. Scientists conduct studies in underground experimental facilities to discover possible particle components of dark matter. Future experiments may increase the chances of directly detecting or interacting with dark matter particles. Future telescopes and observatories may be capable of observing dark matter more precisely. These observations can provide more detailed information about the distribution, motion and interactions of dark matter. These potential advances could offer the chance to expand our knowledge of dark matter and take a significant step toward better understanding the role of this mysterious substance in the universe. Don't forget to subscribe for brand new documentaries and more scientific content.